Very good evening to all respected members. I warmly welcome to day 4 of our faculty development program. In today's FDP session, we are going to discuss about different types of communication protocols and a few note on importance of sensors and its primary functions in industrial robotics. In today's session, we will explore how sensors communicate with controllers using analog and digital interfaces. In addition to that, we will also cover signal conditioning, analog to digital conversion, communication protocols, industrial input-output standards, and practical sensor integration techniques. Let us begin our learning journey for today's faculty development program. Let us have the program overview at a glance. Today's session primarily focuses on converting the raw sensor signals into a meaningful information for intelligent control systems. We will discuss signal conditioning techniques. Followed by that, we will have an understanding on ADC and DAC concepts, that is digital to analog conversion and analog to digital conversion. Comparing different communication protocols such as 12C communication protocol standards, single serial peripheral interface SPI, and universal asynchronous receiver transmitter protocol standards. Then next, in the middle of the presentation, we will be discussing about different standards, input and output standards used for industrial automation. Along with that, we will discuss some case studies and its applications. Let us recap the previous FDP session before proceeding with the day 4 topics. So on day 1, we saw the basic fundamentals of industrial robotic system. On day 2, followed by day 1, programming fundamentals and syntax used in robot operation. On day 3, importance of motion programming and path planning. Today, we will integrate all these concepts into a complete sensor interfacing system used in modern automation. Right away, we will move on to the main concept, sensor signal conditioning system. So what it is exactly? Generally, most sensors generate weak or noisy signals that cannot be directly processed. Signal conditioning improves the quality of the signal before digitization. So these are the various processes involved in the signal conditioning mechanism. First one, amplification. So during this process, it is possible to increase the small sensor voltage through amplification. Next, followed by that, filtering. It tries to remove the unwanted electrical noise during signal transmission process. Next one is linearization. Compensates for non-linear sensor characteristics. Last one, isolation. Tries to protect both equipment and operators from electrical faults. So remember one thing, proper signal conditioning is the base foundation of accurate measurement of digital signals. Next, we forward to basic fundamentals of analog to digital conversion and digital to analog conversion. Sensors generally produce analog signals, whereas controllers process the digital information. An analog to digital converter converts incoming analog voltage into a digital values. Higher resolution provides greater measurement accuracy, while sampling rate determines how frequently the signal is being measured. In addition to the digital to analog converter converts the digital commands into analog outputs for actuators such as motors, valves, and heaters. Together, ADC and DAC bridge the gap between the physical and digital worlds. So we have just discriminated the major comparison between ADC and DAC. Next, you will see the different communication protocol standards. First one is serial communication protocol. After digitization, the data must be transferred most efficiently. So there are three common communication protocols are used. Say 12C communication protocol, serial peripheral interface protocol, and universal asynchronous receiver transmitter protocol. Let us see the significant functions of each protocol standards. So 12C communication interface requires only two wires and supports multiple devices using unique addresses. SPI offers high speed using four communication lines and is preferred for high performance applications. UART, Universal Asynchronous Receiver Transmitter Protocol System, is a simple point-to-point communication standards commonly used for GPS modules, Bluetooth devices, and debugging operations. The protocol selection depends upon the speed requirements, wiring complexity, and the application requirements. Let us see in detail. The 12C communication protocol, a two-wire sensor bus. So 12C stands for Inter-Integrated Circuit. It uses two communication lines, SDA for data and SCL for the clock signal. Each sensor connected to the bus has its own unique address. The master controller initiates communication and exchanges the information with individual slave devices. 12C communication protocol standard is widely used because multiple sensors can share the same communication bus, reducing wiring complexity in embedded systems. So next one is SPI and UART. SPI stands for Serial Peripheral Interface. So this kind of communication protocol provides high-speed communication using master input out, multiple input signal output, and slave select lines. So what is exactly these terminologies referred to? The first one is master output slave in. So it actually acts as an outgoing data channel from the main device to the sub device. Next one, multiple input single output. It acts as a smart antenna system where a transmitter uses multiple antennas to send data to a single receiver. It also supports full duplex communication and it is ideal for displays, memory cards, and high-speed sensors. Universal asynchronous receiver transmitter uses only transmit and receive lines. Both communicating devices must operate at the same baud rate. UART, Universal Asynchronous Receiver Transmitter, is most simple, highly reliable, and extensively used in embedded system, debugging, and wireless communication modules. Next, we shall discuss about the microcontroller based sensor interfacing. Successful sensor interfacing follows a systematic process. The sensor signal is then first conditioned, then converted by the analog to digital conversion mechanism, processed by the microcontroller, and finally displayed or transmitted. Engineers should carefully study the sensor datasheets to understand the address registers, timing diagrams, calibration parameters, and communication protocols. Using interrupts or direct memory access, so that improves the efficiency in applications requiring high-speed data acquisition. Next, we shall see the common industrial input-output standards. In industrial automation, robust communication standards are highly essential. Say, for example, 4 to 20 milliamp current loop is widely used because current signals are less affected by the cable resistance over long distance. 4 milliamps represents the live zero condition, while 20 milliamps indicate the full-scale measurement. The digital input-output modules interface field devices such as switches, relays, and sensors with program logic controllers. Proper sourcing, syncing, and electrical isolation ensure reliable industrial operation. So I'm leaving this practical hands-on session to every students and faculty members who are attending the Day 4 Faculty Development Program. In today's practical session, so we are going to discuss about the temperature measurement using these signal conditioning devices. So here you will interface a digital temperature sensor with a microcontroller using 12C protocol. You will also wire the sensor, initialize the communication protocol standards, and read the temperature values, convert them into degrees Celsius, and transmit the data through universal asynchronous receiver transmitter module. Finally, the measured temperature will be verified using a reference thermometer to evaluate the measurement accuracy. So most probably every students might have did this experiment in electronics and instrumentation lab. So thermocouple measurement of temperature using thermocouple. So what are the common interfacing problems in signal conditioning mechanism with the help of the sensors? During implementation, engineers often encounter common communication issues. If an 12C device does not respond, verify the wiring, slave address, and pull-up resistors. If ADC readings fluctuate, improve grounding, shielding, and signal filtering. For universal asynchronous receiver transmitter communication errors, ensure both devices use identical baud rate settings. In SPI communication, serial peripheral interface communication, carefully verify the clock polarity, phase, and chip select timing. So a structured troubleshooting approach greatly reduces debugging time. So here I have just listed out the common signal conditioning problems that are encountered by each uh, devices as listed below. Here are the key takeaways of Day 4 Faculty Development Program. Let us summarize the today's learning. Signal conditioning improves the measurement reliability and quality. ADC resolution and sampling rate determine the digital measurement quality. Select proper communication protocol standards in common, say 12C, SPI, or UART according to the application requirements. 20 to 4 to 20 milliamp current loop remains the preferred industry standards. Finally, systematic troubleshooting helps the engineers to quickly identify the issues and resolve the interfacing problems. So thank you very much for your active participation in day 4 of our faculty development program. I hope today's session has strengthened your understanding of sensors, industrial input-output interfacing systems, and embedded techniques. In our next session, we will build upon these concepts with more advanced applications and real-world automation examples. Have a wonderful day, and I look forward to meeting you in the next session.